Title of our talk is Leveraging Intermediate Forms for Analysis. Myself, I'm Jared Carlson. A.L. Spitz is here. It's my turn to present, so that's who you're stuck with. Andrew Ryder's back home in Boston. He's hanging out with family, so he's stuck with me today. This talk is basically about formal methods. We're talking about analysis, how we're leveraging them with LLVM IR approach, who's using LLVM community tools, informal methods, why you should be using them. We kind of run the gambit. So we're going to talk about a lot of topics. Formal methods, for anyone who doesn't know, are techniques to construct a mathematical model. Okay, this was started in 1969, was the formalized approach in Hoare logic. This was actually preceded by flowchart reasoning. So you see a lot of overlapping interests there. Now, a model is something very near and dear to me because we talk about models, and the best one I can come up with is a particle. And people use particles all the time. It's a basic physics concept. You don't need to have even gone to undergraduate physics college or university, taken a course. You know what a particle is in your mind. Everyone has a picture in their mind of something so small, but it's a spherical little ball. But in reality, there's absolutely no such thing. Right? A particle of dust is dead human skin cells predominantly. If you think about the quintessential particle as an atom, that's not true either. It's an electron shield in different orbitals. So it's a great model. It's extraordinarily successful. Allows us to have very deep conversations. You could actually head up to talk to the plasma physics guys and use particles. They'll be fine with that until they go deeper. Then we're in trouble. That's okay. But most of the engineering approximations we use on a day-to-day basis, whether it's in mechanical engineering, any other fields of engineering, are models. So talk about Maxwell's equations. If anyone's ever seen this, I hope you have. If not, it's okay. Maxwell's equations, this is very deep stuff, electrodynamics. Most of the time when we're talking about circuit analysis, though, we're just using an approximate form. And it's just fine. It works extraordinarily well. If you're talking about F equals ma, that's not even Newton's law. It's incorrect because it doesn't have conservation of mass implied there. But we still use it. We still use it very, very effectively throughout most of our undergraduate careers if you take a physics course. These are just models, and they're very, very useful. So what I'm trying to say here is that whatever engineering branch you might have started in, if you're talking about mechanical engineering, chemical, that modeling approach, that an analytical approach is embedded in the curriculum. CS, it's getting that way, but not quite as much as other engineering disciplines, okay? When you talk about mechanical engineering or chemical or all the rest, the free body diagram is one of the first thing an engineering student has to do, to create a paper pencil model of what actually is happening, all right? So with these things, we can start create approximations that are extraordinarily useful. We drop so much of reality, but we still get an awful lot of things right. So the process starts pretty much the same. Doesn't matter whether you're doing a program or doing engineering, building a plane, right? Pencil, paper, whiteboard, what do you want to do? What do you want to build? In mechanical engineering, where I spent some time in my day way back 20 years ago, we're talking about CAD, numerical simulation. Then we do 3D printing, get a prototype, and then we build it, okay? And software, same start, it's a whiteboard, off we go, pencil, paper. Then we should be using Alloy and Caulk, those kind of tools. These are formal methods of tools, and these are actually becoming industrial strength now. I don't know if anyone's used them. Hopefully you have. Kathleen Fisher put out a great talk in Usenix last year, and she talked about the history of all these tools, how they have now scaled to the point where they are ready to use and be used in industry on a daily basis. Most people skip this step. We just talk about unit tests, and off they go. And then they start deploying, beta testing, and sometimes it works pretty well, but sometimes we have some real logical flaws in our code. Even in software, the term model is usually used in MVC, model view controller. That's not a model. That's the actual implementation, right? So kind of taking shortcuts in our jargon. Formal methods is trying to fix that. All right, you're trying to actually really get to the mathematical underpinnings and understand what you're trying to build, okay? And we have advantages over plasma physicists, or any other engineers for the most part really, because we define the state. When you're trying to build a program, you know what you want to build, and you are defining how your program works. You have a lot more control over the state and what's known and what's unknown than a physicist or most engineers, okay? The variables that are in physics are very complicated usually. We're not usually capturing them particularly well. In computer science, we can catch them actually quite well. The point of that basically is when you take a mechanical engineer and they get an extraordinarily difficult differential equations, Navier-Stokes is a great example of this. Chemical engineering has transport equations and all sorts of things going on. You can replace that with calculational logic and formal methods, okay? Very powerful stuff. And the examples aren't too hard. I mean, an and and an or, those are actual basic building blocks of formal methods, okay? An or can be written as a maximum of 2 elements. Basically, it's a mathematical operation. Same thing with and, okay? Floor, you define it well, it writes itself. So if you do the thinking up front, you apply your logic, you get a good net result. In assignment, most people don't think about this too often, but when you have a pre and post condition, which is something we have to have in these kind of things, these can be used to calculate how you can progress in your program, all right? There's a relatively trivial example here where we have S is the square of n. I've seen these things in papers submitted where people are actually computing the sum over a for loop. There's really no even reason to write the for loop. That's just a mathematical arithmetic trick to actually calculate the constant. So, it's great that sometimes using LLVM tools, we can actually reduce that and say there's no need for the machine to actually execute the for loop. But who's going to fix the developer? How many times are they going to write that source code computing the for loop when they shouldn't even do it in the first place? I mean, you can teach that arithmetic trick to a 4th grader. So, very trivial stuff, but if you do calculations, much more reliable. If it's complex, white paper references are good too, but the more you can isolate your logic from your implementation, the better off you are. And that's our assumption. And a lot of people have done it like that. So, generally, we're trying to write pseudocode, we're trying to write some sort of logical representation of what we want to do. We want to find a model and then verify a model. Okay, this is the model finder, model checker. That's pretty much what we see in the industry. Some other jargon you're going to see if you do formal methods: invariance, which is a true condition for the duration of the program; intervals, it's just a range. Okay, most of these things have kind of terse jargon. No reason to be afraid of that whatsoever. An abstract domain, polyhedral shapes. These are more complicated relationships. You can easily imagine a range, but you have start dependency graphs. Polyhedral shapes give you good representations in terms of possible states. And again, it really is all about just what's the possible state of the program. Linear constraints, fixed point iterations, convergence, boundaries, limits, constraints, all that kind of stuff. That's all I'm going to go over today. I'm going to use these terminologies kind of free, but I don't want to go too deep because I only have a half hour. So in terms of LLVM, LLVM's been imported pretty successfully by a number of people. Maybe you know some of these folks, maybe you don't. Verified LLVM, University of Pennsylvania, ICOS, NASA, SMAC, some other academic folks. It's been building. It's been fairly recent work over the past 3 to 5 years, I'd say. IR is not ideal, but working with IR is ideal. And that's one of the reasons why we're seeing more pickup in the community, more people trying to leverage it. It's an exciting area. The other part that LLVM really works well is people realize people build tools. I mean, modularity of the architecture is key. And one of the problems with FM is you got some very heavyweight tools. If Alloy is relatively easy to learn, you can play with that, and over a couple of weeks, you get pretty dangerous. Coq actually takes some time. You have to actually really set aside some time. Usually people are comfortable with that after they've taken a course. And they really they've been forced to become pretty good. These tools are getting better, but how you integrate them is a real question mark. In terms of the IR specifically, one of the issues we see in terms of using formal methods on LLVM IR is phi nodes. All right, a phi node is a partial disjunction. Okay, the state of that assignment depends on how you got there. So that's fine for very simple relationships, but as we get increasingly increasingly complex dependencies, now this becomes a real problem. And when we started first looking at this, we started, well, maybe we'll try this, maybe we'll try that. Pretty quickly we threw up our hands, started looking through the literature and go, okay, no one's doing this. Everyone's doing approximations. They're splitting, simplifying it. And again, because it's an approximation, because we don't have to actually generate the machine code on our side, it's okay. We're tangential. We're not on the path to machine code. Instruction sets similarly are regularized. We want to simplify as much as we can. Best approximation for analysis, not for the actual implementation. Okay, a good example is get element pointer. We're doing p-shift. And this is pretty common. I mean, a lot of people are doing this. Conditional branch logic, same thing. You're trying to simplify. You're trying to create as many independent domains as you can possibly do. Sorry. All right, in terms of who's doing what, This is a very growing field, especially within the government. Definitely in industry as well, but the government really started this. Kathleen Fisher, I referenced before, she's at Tufts now. She was at DARPA in the HACMS program. NIST is a big player in this, and of course NASA is huge. Reliability and safety is their major concern. Facebook uses Confer. Microsoft invested heavily in SMAC, and we see a lot less blue screen of death, which is good for everybody. So Verified Elm, University of Pennsylvania. Now what these guys did is they used COC to create formalized transformation passes. They only created a few, but this was really nice because they actually verified that their implementation works, does exactly what it's supposed to do, completely safe, small number of passes, so it's a little narrow in scope, but really well done work. They also had to formalize all the semantics. I should say on that one, for example, the undef value in LLVM had to wipe it out. Any kind of ambiguity has to go away. Seahorn, this is a NASA program. Takes programs, you have to insert C code in this part. You're actually inserting functions, your assertions, your assumes, how you want to handle things. You're telling the program, so you're actually mucking with the source in this case. Okay, so you see the assert, for example. This is relatively simplistic. It's relatively easy to work with, but you're doing interval theory. Okay, integers, assumptions, constraints, all that kind of stuff. So more complex relationships are a little problematic with Seahorn. ICOS is the most generic and the most flexible of all the ones we've seen. We're using this in our approach. This is an inference kernel, so this is basic building blocks in terms of analysis. So if you think about like a linear algebra program, this is the stuff that does the Gaussian elimination, this is reduction forms, QR, SVD kind of stuff. This is basic building blocks for analysis, and you can use it however you want to use it. Good stuff. It's being kept up, fairly recently implemented. If you're interested, you can download it. There are other programs at NASA that are going even further, depending on what they want to do. This also does consume LLVM out of the box. In terms of intermediate forms, what they actually want to work with, in terms of if they don't have IR, then we see things like the C intermediate language. Now, the C intermediate language, obviously, is a subset of C. It's kind of cleaned up, but they had to make the same kind of assumptions. Branch points, all that kind of stuff, simplified, okay? And of course, C is pretty tiny. So if you want, you have an even tinier version of that. The binary analysis platform, this was used for the Grand Cyber Challenge for DARPA, Project Mayhem, which won it. This actually can use LLVM IR, but it really uses an intermediate language for analysis. This is dissemination. These guys are doing real-time vulnerability and patching. Okay. The Project Mayhem was working on a very small operating system. It was a minified operating system, so it didn't actually mirror the real world. But in that sense, they still had to build up all their tools for that. And this used an intermediate language to do that. They wanted also SSA form. They wanted to be able to analyze, disseminate, run passes, all that kind of architecture that LLVM does. So they borrowed an awful lot. Even if it isn't specifically LLVM, the ideas from LLVM were something that they wanted to leverage. Oops. Now the ones we're using is back to the ICOS, but mainly because it gives us good control flow. And we're actually interested in those domains so we can separate things out. This is CFG based, so you isolate domains of interest and then be able to analyze within them. We're replacing the phenodes completely. Simplified assignments, conditional branching, all the stuff I talked about is all handled in that transformation. It's not too hard to go from IR to AR though, and vice versa. Now, is it perfect? No, but we're actually moving back and forth relatively easily. All right, so let's talk about a simple example. For this, I'm going to do the Boltzmann method, which is a relatively simple C code. Now, because this is a physics program, this is actually very complicated ideas. And this is one of the reasons I want to bring this one up is because the code is very simple. I'll show it to you in a minute what some of the key sections of the code. But the ideas in the physics are very complex. Lattice Boltzmann method is a gas dynamics equation. This is a very rare equation. In most equations in physics, time is an independent variable. It's a slider. Go backwards and forwards, you don't care. Okay, Boltzmann equation, time is implied. It actually knows that time has to go forward. Entropy is part of the equation. Okay, so it knows irreversibility is something I should obey. Okay, so that's really sophisticated. Again, that's actually still a model. It only models binary collisions. Anything with 3 more molecules colliding at the same time completely passes on. Very successful, used in industry. It's basically an ideal gas law assumption, but this is used for commercial solvers, used at NASA for rarefied gases. There are different ways to actually implement the computational part. I'm not going to touch on any of those, but very complex ideas, and the implementation looks very simple. Okay, you basically have old school C code. All right, this is one of the things when I talked about, like for example, earlier with the for loops for a sum. The magic here is in the computed constants. The physics is all in the math done up front. So when you put it in, and if you want to do the craftsmanship of code, the craftsmanship was being able to figure out how to put this in a form that is easily transportable to a quick code. This is old, this is computational code. I would call a computer because it computes. This just computes and runs like crazy. So, by the way, if anyone's interested, this is computing equilibriums, which is used to understand how the collisions are going. And this is a very simple lattice. There's no turbulence either in this one. But the way we check a Lattice Boltzmann code is not usually to write tests, unit tests. It's not usually a software engineer checking. Because it's a physics code, we're usually testing it through physics. Simple cases, conservation of mass, conservation of momentum. Okay? What usually happens is a grad student will try and code this up, and they'll have some errors. Depending on their background in computer science, they might have implemented an array wrong or a floating point. Any sort of trivial bug can happen. The way they'll catch it is just looking at, is my mass constant? If I'm not adding energy to the system, is momentum constant for the system at different nodes? Is mass constant? Then I'm good. Then they can actually start getting more interesting. That's the way they'll do it. That is giving us good pre and post conditions. You have very complex physics and gives us really simple pre and post to see what is actually happening. So this is one of the points where we talk about, we take something like SIL, which has high-level concepts supposed to be in the source. It's difficult to take graduate-level physics and put it into source code in a meaningful way. So we actually try to say, okay, you could try and embed it with the source, but it's probably not the optimal way to do that. And this led us to Alloy, which is one of the tools for formal methods we mentioned earlier. Alloy is completely separate, and you can start to write your models in that separate form outside of the source and leave your model separate to the actual implementation. All right, Alloy is only first order. There's actually some recent extensions do second order. We didn't really even muck around with that for the most part. And this is all at MIT for the most part. They just distribute it as a jar. It's very easy to use, good visual interface, like I said, but it's only a model finder. And it doesn't interact with the code, no verification. You can't hook it up to a pass because it's Java. It really isn't meant to work with LLVM or anything like that. So we had our work kind of cut out for us to do something with it. So what we did is we took a subset of the grammar and started implementing Bison parser, ingesting that, generating IR, generating AR from that, and actually looking at that from both a SAT solver point of view, see what kind of satisfiability constraints we can come up with, as well as actually seeing how we could actually inject code in there or check things through symbolic execution. So now, one of the things that we're lacking, and this is probably the key point if someone who is a real backer of Alloy, is Alloy is really meant to find that model and explore it because it's interactive, it's an interpretive environment. Alloy is really meant to go in there and find that model, help you explore. Maybe there's ways to improve it, give you visual representation, simple graph, and have some fun with it. We're not doing any of that. And that's a real problem because we're just doing more of the checking part and understand the first part of finding it, first order solving. That's basically due to resources. So here's our AST that we're consuming. This is pretty simple stuff. We're really not having to do a whole lot. We have signature, which is an object. These all boil down to expressions which contain relationships. These, again, logical relationships in terms of what belongs to what have constraints we have. We introduced a hint because that gives us inline capabilities. We can actually inject that directly to an LLVM pass and have that run as is. Basically, kind of an equivalent of inline assembly. For our model, this is just a snippet, but it really doesn't need to be all that complicated, especially for computational code. We're just talking about densities, masses, momentums, all that kind of stuff. Not that hard. The way we instrumented the code is just use simple annotations. For folks who are interested, there's some nice tricks to actually automate passes that you can just run the code through and we can match the metadata and start looking for model matches and actually start doing analysis. So this is relatively lightweight. This is kind of hacky, but it works. And sometimes you have to get things done. So we leveraged that trick. We got some passes that match IR metadata, and then we compare AR. and we can look for symbolic execution. In the case for mass momentum, symbolic execution gives us everything right then and there. We can actually use the seed data and start iterating there and do a couple of just quick runs, and we say, okay, it conserves. And that's really all you want to do in the code itself. I mean, you don't really care if it conserves mass. Once it conserves mass, you know it's going to conserve mass the entire time. So what we do for the functions, and specifically that are annotated, we just break them up into separate domains, then we can actually dive deeper. This is a relatively tried and true method. Most people try to separate these things into the independent domains. Smaller analysis is better for probing what's going on. The point here is we don't want to test everything, especially in something like the Lattice Boltzmann code. If we have something that's really complicated, there's really only 3 or 4 functions that are of strong interest. Those are the ones we want to test and instrument. So we use passes. Could be something other than that we could use. It's quite obvious. Other people have tried separate tools, but we were very happy with the pass approach. The CFG approach worked pretty well for us because we were able to extract it and work with it pretty well. And the IR, because we can transform and analyze it so well, that was really good. Again, simplification approximations are an issue in terms of going back to IR from AR, but we'll get to that at some point. So this is kind of just a high-level schematic of what's going on. The source composite, we are basically totally tangential to the compilation. We ingest our spec. We started going through that, looking at using Z3. Alloy actually has a number of solvers they can use. We don't really bother with that for now. We'll see how we can integrate later on. Once we have this bidirectional kind of difference we can look at, we can start to look for what are inconsistent between the model and the actual implementation. So for us, we basically boil down to diffs. Now this is nice because we get a result, but this, for our case in the Lattice Boltzmann code for this example, it's fairly trivial because you have very simple conditions, okay? If you have more complex relationships, a diff does not work. That's something we have to work on, and it's one of our issues. So we have a buggy alloy ingestion. We have AR processing and all that, but we still actually get something to work in the sense that we can check very sophisticated code and see if it actually obeys the laws of physics over different iterations and instrument it. And we understand how the IR needs to be transformed to work with that. Again, we're only analyzing critical sections of the code. Our biggest issue is that if we fail, we don't inform people. And that's a real serious issue because one of the reasons we talk to most developers, they will use Clang because they like the error message. That diagnostic engine gives them ways to fix things. This is something we need to get much better at. There are tools, but when working in their environment, you get their own syntax. For us, trying to understand where the implementation breaks versus the model and who's right, who's wrong, that's the problem we're having. So, as I said, we can diff. Most of the original results on the Lattice Boltzmann code is really through symbolic execution, okay? That doesn't have to be. You could look through different constraints and understand who's doing what logic is inconsistent. But symbolic execution works. That's also what Seahorn does as well. Even for just simple integer relationships, Seahorn uses symbolic execution the vast majority of the time. And friendly errors is just something we absolutely need to have. So, kind of wrapping this up, but modeling language, that's something we can play with. Alloy is something we like because it's relatively simple. It's also relatively consistent. Alloy borrows from Z, which is a specification language. You can do whatever kind of language you want, but there's a consistency within the field, so we just adopted that. We used a physics code because it's nice, it has very good, strong ideas that are hard to put in source code, and we can actually separate the two. We feel that's justified. And then you can interact with the code in terms of whether we want to analyze the logic or analyze the code itself. So, and on that, I think one thing I need to say. While this is a growing field, one of the big issues we have is, formal methods talks to compiler folks in here and there, but the usability of the two tools and how they work together is something we definitely need to address. We're happy to talk about formal methods to compiler people, but it's also necessary to talk to people in formal methods and say, you need to go to compiler people and get better tools and understand their tools better. You want to get formal methods used, you have to get them as part of the actual software process and the tool chain. And with that, we're done. So thank you very much. Sure.
Any questions?
So in your code, there is lots of floating points. And the property that you kind of defined and that you were checking depends on these floating point computations.
Yeah.
I think I saw lots of doubles, right? So I'm pretty sure that Alloy has no support for floating points. So how do you, I don't understand even how you check the code.
Symbolic execution gives us ability, resolution for, we updated that to doubles in there for double precision, but we can just check within the relative error bounds for symbolic execution over a few iterations.
Could you repeat this? I didn't.
We do symbolic execution.
Symbolic execution invokes SMT solvers, right?
Well, we're actually seeding the computational equilibrium, right? We have the lattice as it's set up, and we can execute that over an iteration.
And you take floating point errors into account? So what is the lattice? I don't understand what the lattice is.
The lattice, okay, so in the Lattice Boltzmann code, right, you have directionalities that can go, gas can go in different directions. And go up, down, left, right. For a 2D lattice, it's just got 8 directions and rest, okay? So when you have a distribution, the gas can move along and propagate. At each node, that should sum to what it was before if you're not introducing any new mass. And if you're not introducing momentum, then as you sum around and multiply times velocities, you should have a consistent value.
Yeah, I understand, but these are all floating point computations. And floating point errors happen during these computations. So I'm not sure how you match that the mass is being preserved, which is also floating point computation, against when all these things are actually computed, which is also floating computation, right? I mean, how do you model floating points? It's totally unclear to me in your approach. But anyways, maybe we should take this offline.
Yeah, we can talk outside, it's fine.
Yeah.
Anyone else?
All right, thank you.
Thank you.